Okay, today we talk about the double refraction at the boundary between, say, air and a crystal. Okay, before we discuss how the light bends inside the crystal, let me show you how to understand the refraction phenomena for the light bending into an isotropic medium. So, in isotropic medium, such like gas, water, air. Okay, we have a fixed, constant refractive index, and so if we consider a beam of light incident from medium 1, medium number 1, characterized by the permittivity epsilon 1, permeability mu 1, and the medium 2 characterized by permittivity epsilon 2, permeability mu 2. Then light bend according to the so-called Snell's law. Here, N medium 1 has the refracting index N1, medium 2 refracting index N2. And the Snell's law is written as this. Okay. How to understand Snell's law? You have at least 2 different ways to derive this result. The first method, you use the so-called Fermat's principle. Okay, according to Fermat's principle, light goes through a path, along a path that takes the shortest time. Okay, for example, we have light start here, point A, and end here, point B. Which way the light goes, light which propagate. You just study all kinds of paths that takes the shortest time. Then you finally find the correct path, follow this law. This is the so-called Fermat's principle. In fact, light does not take the shortest time path. Light propagates in this way because if we consider a path a little bit different from the so-called correct path, the phase aggregation of the light are almost the same, just like it goes along the correct path. Okay. However, if we take a different path, then light, you know light is a wave, okay? Then if we take this path and calculate the phase difference aggregated from A to B, then if you move outside a little bit, you get very different phase aggregation. So light will destructively interference here, and so we cannot see the final result of a specific path. However, along this correct path, a little bit different position of the path will give you almost the same phase aggregation. So light interference with each other constructively. So you can see a very specific path. So what Fermat's principle really said is that light can constructively interfere with each other along the so-called correct path. You can learn the details from a very interesting book by Richard Feynman. Richard P. Feynman. Feynman is a great physicist and also a great educator. He gave a series of talks in New Zealand about QED, quantum electrodynamics. In those lectures, Feynman explained in details what really does Fermat's principle say. And you can find the book. Its name is QED, Strange Theory of Light。我印象中应该是叫这个名字哈，名字有可能记错哈，但是呢，这个是一个很好的一本书，我觉得还蛮不错。它基本上没有用到什么数学哈。This book almost almost no mathematics are used in this book. Okay, and Feynman just use some metaphor and explain the details of why light bend in this way. Okay. However, this kind of thinking cannot help us to understand the light bending in a crystal. So we use another strategy. The different method to obtain this Snell's law is using the Maxwell's equation. According to Maxwell's equations, if you want to understand what does Snell's law mean, you can just consider an incident plane wave. A plane wave incident from medium 1. And we know there must be some reflection. So we have the refracted beam. And there must be refraction beam. Okay? Suppose the incident light has wave vector k1, and the reflected light has wave vector k1 prime, and the refracted beam has wave vector k2. Okay, and here we have theta 1, theta 1 prime, and theta 2. Okay. And then, according to Maxwell equation, you know what Maxwell equation is. Maxwell equations include these 4 equations. For usual optical material, we set rho to be 0 and J to be 0. No current density and no charge density. Okay, and we assume a monochromatic wave, which means that the wave vibrates with a specific frequency, angular frequency omega. Okay, so we have already learned in chapter 1 that we can use the complex vector representation to represent the field quantities, and everything inside everything can be written like this. Say ERT can be written as some ER times exponential minus I omega t. Okay. Here I allowed this ER to be not plane wave, okay, because we can add different plane waves to get the final field, which does not behave like a plane wave. Okay, so this form in general is complex vector, and for this kind of complex vector, when we do the time derivative, we get say I omega times the quantity. So I can write here as minus I omega times B. And here we can write the result as I omega times D. Okay. We know in chapter 1 that we can derive the so-called boundary condition. To connect the field in medium 1 to the field in medium 2. The boundary condition corresponding to the 4 different field quantities are the connection of dn1, dn2. N means normal component, okay? The normal component Bn1 is equal to Bn2, and the tangential component of Et1 is equal to Et2, and Ht1 is equal to Ht2. The tangential component of E and H are connected along the surface, okay, on the 2 sides of the surface. And if you read some textbook to the authors derive the reflection and refraction coefficient, you will see that most of the book do not use these 2 boundary conditions. Okay, that's because when we have a non-zero frequency and we consider a monochromatic wave, from this result, we know that B is proportional to curl E, and D is proportional to curl H. And according to vector analysis, we know that the divergence of curl is just equal to 0. So we can get divergence B equal to 0 automatically, and we also can find divergence D equal to 0 automatically, because now D is proportional to a curl of some vector, and B is proportional to the curl of some vector field. Okay? So that's why we do not need to use any consequence derived from these 2 divergence equations. So now these 2 equations become redundant because it satisfies automatically if curl is proportional to B and the curl H is proportional to D. That's why in most of the textbook, when you see they derive the refraction coefficient, they do not use these two boundary conditions. Just use these two boundary conditions. Okay? So, according to these two boundary conditions, what other consequence we can obtain? You see that in the medium one part, the field includes two parts, say E1t times exponential I omega t minus K1 dot R. Okay, we consider the tangential component plus E prime 1t exponential I omega t minus K1 prime dot R. Okay, and in the number 2 medium side, we have E2t times exponential I omega t minus K2 dot R. And all the quantities are evaluated on the surface. Surface means, say this is the x-axis and this is the z-axis. So only the kx component need to be considered because now we set the surface to be z equal to 0. Okay, so originally we have k1x, k1y, k1z, and in fact these three k's are lying on the same plane. Say y equal to 0. The plane is y equal to 0. And along this line, we have z equal to 0. So ky, kz will not appear in the result. So here we have k1x times x. We have k1 prime x times x. And here we have k2x times x. Okay. So when you compare them, you can very easily find the relation that we must have k1x equal to k1 prime x equal to k2x. Okay? We have to have this restriction, so this equation can be satisfied. Okay? And what does this equation mean? What does this equation mean? We know that k1 x is omega over c times n1, the magnitude, times the sine theta. Okay? And k2x is omega over c times n1. No, k1x prime is also equal to this quantity. Okay? And k2x is omega over c times n2 times sine theta. Okay. So this equality finally gives us this result. So since now they have the same omega of c, omega of c, omega of c, so we find that this equality gives us sine theta 1 equal to sine theta 1 prime. And this equality gives us n1 sine theta 1 equal to n2 sine theta 2. Okay? So this tells us that theta 1 is equal to theta 1 prime, which means that the reflection, for the reflection beam, the angle is the same as the incident angle, okay? And the second equation is just the Snell's law. Okay, so we see what is Snell's law. Snell's law, in fact, means the phase connection condition. Okay, the phase across this interface must be the same. Okay, on this side and on this side, the wave have the same phase. The same phase to promise that the wave can be connected according to the condition. Okay. 所以施耐尔定律的意思是什么？其实就是相位连续的条件啊，相位连续的条件啊。So now we understand what Snell's law tells us. Then we apply this idea to an isotropic medium. Now we consider an isotropic medium. Say the crystal, okay? We have already learned that for the crystal we have the so-called normal surface, which means that the collection of the K vector for a chosen frequency omega, okay? So for example, we know in general the normal surface is a two-shell structure. Say they have the two shells. Okay. And here, this line indicates the interface. And here represent the origin of K vector. Okay. So here this is the normal surface. Of the crystal. And for light inside, say, water or air or glass, we also have the corresponding normal surface, which is a very simple sphere. We denote the refractive index as n0. Okay. Then suppose we consider an incident light having this K vector, K0. Then we calculate the projection. The projection K0x. Okay? And then we know that Snell's law means keeping the tangential component of the K vector unaltered. So we take this segment KOX and we see what kind of K vector inside the corresponding to this projection when we use the normal surface. We see that there are two different K vector. There are two different K vector corresponding to the same projection K0x. Okay? So using this method, we finally find the refraction beam. Okay. This is the K vector corresponding to the first refracted beam, and this is the second wave vector corresponding to the second refracted beam. If we want to know not the phase propagation direction but the energy propagation direction, we need to take the gradient, which means the direction normal to the normal surface locally. Here. We use these two orange arrows to find the propagation direction of the beam inside the crystal. Okay. 所以这边的意思就是说，什么叫做施奈尔定律呢？施奈尔定律其实就是相位连续的条件啊，相位连续。那我们要保证相位连续，其实就是要保证 K vector 在这个交界面的投影的这一段长度是固定的啊，所以我们就取一样的长度，然后去问 normal surface 上面什么样的 K 会对应到这个投影，然后我们就会找到两个不同的 K。 然后这两个不同的 K 呢，给出了两个特殊的点。然后如果我们需要知道能量往哪里传，我们就根据这两个点的附近啊这边的曲面去找它的 normal 法向量方向。那这法向量方向就是 beam 的能量传播的方向。OK， 好，那我这个图画的是能量跟 K 好像是同样方向，这是因为我刚好画成像圆的样子。但是如果我画的不是圆的样子的时候，它可以是不同方向啊。In general, the normal surface may be a little bit different, may look a little bit different from this standard form. Okay, say, suppose the normal surface looks like this, then we will encounter a very interesting phenomenon. Suppose we have a beam incident normally. Then this means that the tangential component of the K vector is equal to 0. So we just find this point and this point. Okay. Then according to this point, the light still propagates downside, and at this point downward, and at this point the normal vector along a different direction. So this means that even we send a beam of light normally to the crystal, it may happen that it becomes two beams. The first beam goes straight along the original direction, and the second beam goes along a different direction. And usually we call this O ray, and this is called E ray. Okay.好，我现在呢画一个更具体的，我们考虑一个 uniaxial crystal 啊 ，we consider uniaxial crystal. We consider uniaxial crystal with the optic axis along this direction. Okay, this is the optic axis. Optic axis. Then we consider this situation, we send a beam of light along this direction, which is normal to the interface. Okay, and suppose we send a beam of light along this direction. Send a beam of unpolarized light. Unpolarized light. Okay. And unpolarized light has two possibilities to be polarized. The first possibility is that it can be polarized along this direction, which is normal to the black hole. Then this corresponds to the so-called O ray because the E vector is perpendicular to the optic axis, so it behaves just like the usual light in isotropic medium. So it goes along the straight line like this. However, we can also have another polarization. Suppose the D vector is perpendicular to the beam. We learned that dn1 is equal to dn2. So for this beam, since D vector is parallel to the interface, there is no normal component of D vector, which means dn1 is equal to 0. So dn2 is also equal to 0. So this means that after penetration through this crystal, the D vector will keep pointing upward. D vector will keep along this direction. However, for uniaxial crystal, we have epsilon along the optic axis to be epsilon E, and epsilon along the direction perpendicular to the optic axis to be epsilon O. Epsilon E and epsilon O are different. So for a D vector, along this direction, since epsilon E and epsilon O are different, we usually will get an E vector along different direction. Okay. 因为你分解出两个分量的 epsilon 不一样 ，OK， 然后你除以不同的 epsilon， 就得到不同的 E 分量，叠加出来的 E 就会跟 D 不同的方向。So if you have a D vector along a different direction, then since the H vector connected directly into this crystal, H vector is along this direction outside this backbone. So E cross H gives you pointing vector along this direction. So this means that the first beam goes along this path, the second beam goes along this path. OK， 就说你会有一束光分成两束光，那这个就是 O ray， O wave， 这个就是 E ray，E wave。OK， 好，就是你可以有一个斜的光轴，然后你正向入射一道光，它就分成两束。好，那这两束所对应到的这个 polarization 是不一样的。第一束它的 polarization 电场是指向黑板外面的，那第二束呢，它的 polarization 会落在黑板上，啊，但是它的方向会跟 D vector 不一样，啊，然后因为 D vector 保持了它是垂直的这个向上的方向，那又因为呢沿光轴跟垂直光轴的 epsilon 不同，所以导致你进到 crystal 之后的电场方向会跟 朝上的方向不一样，会偏转一个方向。那它的偏转就会导致 Pointing Vector 的偏转。那 Pointing Vector 代表能量流动的方向，所以你就看到两处壁，好，所以就变成 E-ray O-ray。这是用电磁场观念去解释，而这个是用 normal surface 去解释，好，但是其实都可以得到同样的结果，好。So we can use two different methods to explain this very interesting phenomenon called double refraction. Double refraction, OK. 好，那我们可以看到有一些插图，我们来看一下哈，就是在 Figure 4至7。我们看那个 positive uniaxial crystal 就好哈。We see the left hand side the positive uniaxial crystal.好，这时候呢，你的那个有几种可能状况。positive 的意思就是你的那个椭球比那个球还大哈。So for positive uniaxial crystal, for positive uniaxial crystal, we have NE larger than NO, and this implies that normal surface has this shape. The surface consists of one sphere and one ellipsoid. The ellipsoid is formed by rotating this ellipse along around this axis. Okay. Then this direction is the so-called optic axis. So we have different situation that give us different possible refraction results. First, we consider the situation that is the optic axis. Usually we call it C-axis. C-axis is just the optic axis. So if C-axis is along this line, then the refraction for this case we get two refractive beams. The first beam, this corresponds to the sphere, is the O ray, O wave, okay? O wave. O wave have the polarization perpendicular to the C-axis. So for O wave, the polarization of the E vector is the direction point outside of the backbone. This is the O wave or O ray. And for the second possibility, we have the E vector lying on the backbone. This is the E ray or E wave. In the middle of figure 4.7, we see that we consider the situation that the z-axis is pointing upwards. Okay, then this is O, this is E. Okay, and for O, we still have coalition pointing outwards, and E lying in the plane. Okay, and finally, we have this possibility. Here we have the z-axis pointing outside of this backbone, and for O ray, we must have the E vector perpendicular to the optic axis. Since now optic axis is pointing outward, so for O ray, the E vector is polarized, is lying on this backbone. Okay? And for E ray, it has the E vector parallel to the z-axis. You can also plot the similar refracted beams by considering the negative uniaxial crystal. Negative means negative means NE is smaller than NO, and corresponding normal surface looks like this. The corresponding normal surface for negative uniaxial crystal looks like this. Okay. And this direction is the optic axis or z-axis. And the normal surface consists of one sphere and one ellipsoid. Okay, and both of them are formed by rotating the corresponding curve around this z-axis. Okay, 好，所以你也可以对这个 negative uniaxial crystal 的 normal surface 去画同样的这个情况，去画同样的这个折射的情况。好，那到这边为止的话，我们大致上把这个 uniaxial crystal 的这个 double refraction 呢，大致讲清楚啊。但实际上，这个 double refraction 并不限定是 uniaxial crystal 啊，它其实也是可以是 biaxial crystal。但我们下一堂课之后，我们会再继续讲 biaxial crystal 有一个更有趣的现象，叫做 conic refraction 啊。So up to now, we have already mentioned the details about light bending inside a uniaxial crystal. Okay. However, we can use the same strategy to find the refracted beams inside biaxial crystal. So in general, we can use the same method to find the看一下画下。 Okay. For biaxial crystal, you may encounter normal surface like this. Then you can still use the same method to find the corresponding refracted beam in biaxial crystal. However, what is most interesting about the biaxial crystal is this specific point. We know that for biaxial crystal, the normal surface intersect with a 3K plane. Suppose we assume nx is smaller than ny is smaller than nz. Then in the kx-kz plane, we get the intersection of the normal surface with the coordinate plane to be one circle and one ellipse. And we know that if we connect this point with this point, connect this point with this point, we have two optic axes. For biaxial crystal, we have two optic axes. Then, in the vicinity of this point, we will see that locally, this surface looks just like a cone. And for a cone, if we consider beam of light, then we will encounter a very strange phenomenon called conic refraction. And I will explain the detail next hour. 好，我们这边就先休息一下。